Have you ever just stopped and thought about how wild it is that our planet has the perfect temperature for life? I mean, we're whipping through the absolute freezing cold of space, all while circling a star that's basically a giant nuclear furnace. So let's get into the incredible balancing act that makes it all work: Earth's solar energy budget.
It really is a great question, isn't it? You've got this insane heat source on one side and this infinite icy void on the other. How in the world does Earth manage to find that Goldilocks zone, that just right temperature where life can flourish? Well, the secret is all about how our planet manages its energy.
So to get to the bottom of this, we've got to start with the source of all the energy. And that brings us to the star of our show, pun intended, the energy that's actually delivered from the sun. It's got a proper name, and it's a really important one to know: insolation.
Now, insolation sounds a little technical, but it's really just the term for all the sunlight and energy that makes it to our planet. This energy travels in the form of short waves, and it's what powers, well, basically everything, from our weather patterns to the plants that grow our food. You can think of it as the income side of our planet's energy account.
And just to give you a sense of scale here, check this out. The sun is blasting an unbelievable amount of energy out in every single direction. But because we're so far away and, relatively tiny, Earth only catches about 2 billionths of it. A super small fraction, but it is more than enough to power our entire world.
Okay, so we've got all this energy coming in. But here's the thing. It doesn't hit the planet evenly. And this variation, this uneven distribution of energy, is precisely why we have seasons. It's all part of this beautiful, predictable dance between the Earth and the sun.
And here's a fun fact that might just flip what you thought you knew about seasons. For those of us in the Northern Hemisphere, our winter is actually when the Earth is closest to the sun, around January 3rd, and we're farthest away during our summer, around July 4th. So right away, that tells us that our distance from the sun isn't the main reason we have seasons.
So if it's not about distance, what is it? Well, it's all about the tilt. Earth's axis is tilted, about 23.5 degrees. So as we make our year-long trip around the sun, that tilt means different parts of the planet get more direct, intense sunlight. On the March equinox, the sun's directly over the equator. Then by the June solstice, it's aimed right at the Tropic of Cancer, giving the Northern Hemisphere summer. It's this tilt that dictates the seasons.
The best way to picture this is with a flashlight, right? If you shine it straight down on a table, you get a really bright, concentrated circle of light. But if you angle that same flashlight, the beam spreads out over a much bigger area, and the light is way less intense. The sun's energy is exactly the same. It smacks the equator head-on, concentrating all that heat, but it glances off the poles at a shallow angle, spreading the same amount of energy over a huge area.
Okay, so we've got uneven heating, we've got seasons, but how does this all add up to a stable temperature? I mean, Earth is constantly soaking up energy from the sun, so why doesn't it just get hotter and hotter and hotter? Well, that's because it has to get rid of that energy too. And this is where we get to the core idea: the heat budget.
And here it is, the formal definition. It's all about the balance. The planet has an income of energy from the sun, and it has an expense of energy that it radiates back out. When those two things are equal, the overall temperature stays stable. It's a really simple concept, but it's one of the most important things about our planet.
Honestly, the easiest way to wrap your head around this is to think about a bank account. It's a perfect analogy. If you deposit more money than you spend, your balance goes up. If you spend more than you deposit, your balance goes down. For Earth's temperature to stay the same, the energy it deposits from the sun has to perfectly match the energy it spends back out to space.
All right, theory is great, but let's make this real. To really get a handle on this budget, we're going to follow the journey of 100 imaginary units of solar energy. We're going to see exactly where every single one of them goes. So let's set our starting point. Imagine 100 units of solar energy, 100% of the insolation arriving at the very top of Earth's atmosphere. Okay? That's our income. Now let's track the journey.
And right off the bat, not all of that energy even makes it into the system. There's a huge split. Before it can do any heating at all, about 35 of our 100 units get bounced straight back to space. That leaves the remaining 65 units to be absorbed by the Earth and its atmosphere.
This whole reflection process has a name. It's called albedo. It's basically a measure of how reflective something is. And since these 35 units of energy are sent right back out, they play absolutely no role in heating our planet. It's like a paycheck that gets returned to sender before it ever even hits your bank account.
So what's actually doing all this reflecting? Well, the breakdown is pretty surprising.
Of those 35 reflected units, a whopping 27 are bounced back by clouds alone. Dust and other particles in the air get another 6, and the actual surface of the planet, things like ice and snow, only reflects about 2 units. Clouds are by far Earth's most important sun shield, which also means that even tiny changes in how much of the Earth is covered by clouds can have a huge effect.
Okay, so 35 units are gone, reflected back to space. That leaves us with the 65 units that actually get absorbed. This is the energy that does all the work, heating our land, our oceans, and our air. So where does it all go?
Let's break down those 65 units. About 14 of them are absorbed directly by the gases in the atmosphere. The rest makes it all the way down to the surface, where 23 units warm up the land, and another 19 warm up the water. Then there's a final 9 units that get absorbed indirectly by the lower atmosphere through things like convection. See? Every single unit is accounted for.
All right, now for the most important part of the whole balancing act, the expenses side. The Earth, now that it's been warmed up, has to get rid of that energy to keep the budget balanced. And it doesn't just reflect the same sunlight back out. Instead, it radiates its own heat in a totally different form, as long-wave infrared radiation, or what we call terrestrial radiation. This change from short-wave sunlight to long-wave heat is the key to the whole system.
So let's just put it all together one last time, nice and simple. 100 units of energy come in. 35 of them are immediately reflected, that's the albedo. The other 65 get absorbed, warming the planet. Then, to balance things out, those exact same 65 units are radiated back out into space as heat. The income equals the expenses. The budget is perfectly balanced, and that's what keeps our planet's temperature stable.
For thousands and thousands of years, this system has maintained this incredible, delicate equilibrium, giving us the world that we know today. And that, of course, leaves us with one final and really important question to think about. What happens if something changes? What happens if less of that outgoing heat is allowed to escape, and this perfect budget suddenly becomes unbalanced?